So now we'll have a discussion of a simple modeling of dark matter.
Thank you for inviting me. My name is Birrer. This work is in close cooperation with Simon Lilly. I'm from the Quenching of small machines. Thanks. And I'm going to present you a simple model which should be a very simplified with a very simplified picture of solution. So the spirit is how far can we get by taking two very simplified models together in matching a set of observables over this. And just to get a little bit framework, if you think of the range of models between empirical and physical, we are lying somewhere here, a little on the right of Birrer et al. Models, basically really linked on the dark matter side. We mostly, our models came from the galaxy evolution and see then how the observables happen. So, a model of a galaxy, a simple picture, so these are dark matter halos. We imagine it in a very simple model. And there are two regions, is the outer region and the inner region. Inner region is the active region of the star formation going in all these processes, and the outer space is just there might be some gas. Physics we're doing is basically merging the picture of dark matter evolution. This is dark matter physics. We apply here merge theory based on extended perceptive theory, and then here an interaction inner outer and specifically inner side. Baryonic physics. That's how we split it. So a galaxy regulation system we had heard very nice one before on a very simple regulation review. We applied one from Lilly et al. 2013. Basically, its main part is gas has a certain efficiency to turn into, or get a star formation rate out, get an outflow load, and complete the continuity equation of really the basis of this model. So the change in gas has also an inflow coming from outside. I will talk about it in a minute. Another thing we need, as observation tells us, the red and blue galaxies quench an active galaxy. We need, in addition, some quenching formulas. And here we applied the model from Peng et al. 2010, and it's follow-up paper 2012. Basically, here the stellar mass function of the red and blue population derives from how one can relate it to some mass, which is this function, stellar mass. And we also showed this relativity between mass and environment. And so, for accounting for increased fraction of red satellites in
Can you hear me? Yeah.
Sorry.
Yeah. So this is about quenching. So please, this is a very phenomenological description. It's not meant to be the explanation of what quenching is. It provides us with a description, is well written here, that is designed to match observables. Just to make sure we understand this. So the model, the simple concept. So it's simple differential equations embedded in a dark matter merger tree that basically allows us to perform this calculations on the entire age of the universe. It's basically, the main thing is the local continuity in stellar, gas, and dark matter. So every single galaxy, every single halo, we basically enforce continuity. And we apply quenching as a one-way process. Once it's quenched, the galaxy stays quenched, doesn't form any stars anymore, but the overlying dark matter is still evolving. And so we are able, with such a model, to predict stellar gas, dark matter mass, and also its derivative, star formation rate, and so forth, for every single galaxy of a representative sample of the universe, for basically all redshift here from redshift 8 to 0. That's what we're able to make prediction out of it. So, results. So the simplest model. So coming back to the gas inflow, turns out to be a very crucial thing in our model. So if we just say the gas inflow follows the dark matter accretion history, so if dark matter halo grows, the same specific rate, also the gas inflow comes into play. And so basically we have a direct link between the dark matter and the baryonic inflow into this active region. So what is the result? Here we have, similar to one Birrer et al. 2013, so on the x-axis time since Big Bang, so Big Bang is somewhere here, we are here. Here is halo mass log scale, and basically in color here is amount of stars formed per unit time per unit halo mass. And what we get out here is very consistent that around the redshift of 2, around 10 to the 12 in halo mass, most of the stars are actually formed, which is a direct output of this model, and below like 10 to the 10.5 or so, and very minor stellar populations are grown. So far on this very qualitative side. We can also be very quantitative. So if you look at a specific star formation rate history as a function of redshift, we slightly underpredict the noon, the cosmic noon at redshift 2. The same for the star formation rate density. We don't get here a factor of 10 out of it. And what we get here for stellar mass function, what we get is 2 mass functions. So we have a red and a blue mass function in total. And we have here a slight mismatch if we just take this zero-ordered model. So,
what's quenching stuff? I can't.
Pardon me?
What's causing things to be red? I missed that.
We apply the rule of Peng et al. 2010, and this is just a probability. If you form star, you assign a probability that this galaxy is going to be quenched. This enforces the exponential cutoff in the main sequence population. That's the main motivation for this law. So we can tune it as every model, and so we really focus here on the gas inflow. It turns out we also played around with others. It doesn't really matter so much, and we might mess up with other observables. So, and then we can see here the red line. We can go through the data points of Stark et al. In the specific star formation rate. We also get the scalings up for the star formation rate density, and for the stellar mass function here shown at redshift 0, we basically match the red and the blue population. What we also do, remember, we solve these equations within a dark matter framework. So we have to all this observable, we have to link to the dark matter halo. So let's look at it for this tuned model, and this is the result. Blue dots are our central galaxies, active central galaxies. Red dots are our passive central galaxies. Here we have mean relations overplotted, the Birrer et al. Compilation. And interesting, here the dashed green line is the cosmic baryonic fraction. So that's basically the amount of baryon one has per halo that potentially is able to form stars out of it.
So what's the magnitude of the scatter at the mass event?
Here?
Yeah.
Well, yeah, this is a sample. So roughly, it's 0.5 dex. So could show you a slice through here, but yeah, this is the point. So, and what you crucially see here is that it's a very steep relation, and without quenching it would basically, what happens, thank you, it can't get above here, so it will get very flat here. It's still forming stars, but it doesn't happen, so it doesn't flatten as one might expect. Just before it's supposed to flatten, we actually have to put in quite a lot of gas to keep it steep, and just before it runs out of gas, quenching turns in. the description we apply from Peng et al. And in that sense, what we applied is a regulator that has nothing to do with quenching, a quenching law of Peng et al. That has nothing to do with regulation and just says at a certain stellar mass you have probabilities to get quenched. Both together leads to a coincidence that we're very close to violating continuity. We're not violating here, never violating continuity, but basically just at the right moment quenching turns in such we can ensure and match the population of the universe. So to summarize here, we have here a simple model, a combination of regulation and quenching, and it gives remarkable consistencies with various observables. The crucial thing is the gas inflow, re-injection of the gas, how you assign them to the really active region. And strikingly, quenching occurs just when galaxies approaching their maximum conversion efficiency in turning gas into stars. Yeah. I'll leave you with that. Thank you.
So we have a few minutes for questions. Peter, please.
I'll just say one. So the magnitude of the scatter is worrying to me because we actually know from observations that the scatter is probably more like 0.2x. You know what the mass event is probably less than the 0.5x you said, but it does look pretty large at around 10 to 12. I think we have constraints pretty close to there that say the scatter should be less than 0.5x. And so that may mean you're not really getting up all the way to the baryon fraction in terms
Yeah.
of stars.
Yeah. So here we have applied a completely random quenching process linked to stellar mass. So whether there's another correlation to whatever causes quenching might, of course, also affect the scatter in that. And I mean, here it's quite high, but even if it's a factor of 4, you also have some gas in the galaxy. You have satellite galaxy. You end up quite close to actually what you potentially be able to form stars. But yeah.
So I had a quick question. So you said that you had to futz with the accretion rate, the gas accretion rate compared to the dark matter accretion rate. What was the form of that? Like, what did you have to do to make it work?
To do is just before here it quench, you have to basically push in all the gas that is in the halo. Basically have to here make a very efficient infall of the gas into the central active region is one thing. And then you have to delay gas infall at the very early stage of the universe, such that later on I get a higher specific rate of growing the galaxies, and also in total effective rate at around redshift 2 that it peaks there, that we have to give a little bit more efficient star formation there. So like 3 things, but different things to tune, but together without violating continuity gives rise to all effects.
Are there any other questions? Thank you, sir.
Thank you.